I'd like to go over the mechanism for the formation of the acyl chloride from a carboxylic acid. Now, as we've already mentioned, acyl chlorides are the least stable of the carboxylic acid derivatives. So you cannot make an acyl chloride from an acid anhydride, an ester, or an amide. You can never make something that is more stable, make something less stable in one chemical reaction step. Now, one thing we can do is use the carboxylic acid. The carboxylic acid is kind of versatile in that we can use it to make any of the other derivatives. So we're going to start with a very basic carboxylic acid. We're going to start with acetic acid. And keep it very simple. And what we're going to react it with is thionyl chloride. Thionyl chloride is very similar to our carboxylic acids, except for we don't really have a carbonyl carbon. We have a sulfur instead. But it reacts very much the same. It is, in terms of its oxidation number, very positive in character. You can't really do any favorable acid-base chemistry here. So, like we've been talking about many times in class, we end up doing electrophile-nucleophile chemistry. And the oxygen of the carboxylic acid actually acts as the nucleophile toward the sulfur. And as this occurs, we break the sulfur-oxygen double bond. And we make a new intermediate. So this intermediate that we're going to make it's got some positive charge and some negative charge. So it's overall still going to be neutral. But our pseudo-tetrahedral intermediate now is where the sulfur is instead of the carbonyl carbon. Now, I hope you remember whenever we've made these tetrahedral intermediates, we try to do proton transfers through solvent if it's useful. In this particular case, it's not going to be because we've actually got some decent leaving groups. Now, I know that the carboxylic acid that we've just added is potentially a fantastic leaving group. It really is. You get a neutral molecule out of that. But the chlorines are also really good leaving groups. They are the corresponding conjugate bases of HCl, which is an awesome acid. So I really don't need to do a proton transfer through solvent here because I've already got 3 really good leaving groups. So at this point in time, I don't really have to do any rearrangements as I reform that pi bond between the sulfur and the oxygen. And I would kick out the chlorine as the leaving group in this particular case. So as that has occurred, I'm going to make a new intermediate for myself. I'm still going to have that protonated oxygen. I haven't done anything with that yet. Now I've got this chloride in the solution. Now I don't want to pick up the proton from the oxygen because that would be generating a really strong acid in a neutral solution. So we don't want to do that. That wouldn't be a good idea for us. But the chloride really is a decent nucleophile, and if I'm not doing acid-base chemistry, I would like to do electrophile-nucleophile chemistry. This chloride really could add to the carbonyl carbon or to the sulfur. You can go backwards. It's fine, but that's not productive. So we're going to show it actually adding to the carbonyl carbon. So lone pair electrons add to carbonyl carbon. You can't have 5 bonds, so we break the pi bond to the oxygen. Now at this point we're making a tetrahedral intermediate at the carbonyl carbon. So this is the intermediate we have at this moment in time. Now, as we mentioned a moment ago, we really like to reform pi bonds if we can and kick out leaving groups. So this oxygen is going to come in and reform this pi bond. And you do have two potential leaving groups in the chloride and in the oxygen, because if you kick out the oxygen, you're kicking out a neutral molecule. If you kick out the chlorine, you're kicking out a decent leaving group. I mean, again, it's the corresponding conjugate base of a strong acid. So honestly, either one of these two groups could go. If I kick out the chlorine, though, I'm going back where I came from, and that's not productive chemistry. So we're going to show the carbon-oxygen bond breaking, and again, oxygen is the more electronegative group, so oxygen will take the electrons with it. Now, after all of this has actually occurred, lo and behold, we've made the acyl chloride, which is our goal. This is how it's done. The other part of our reaction at this moment in time is not that important to us, but it's there. Okay. And what it does is it will decompose eventually into sulfur dioxide, which is a gas that floats out of the container, and hydrochloric acid. So this is how we make the acyl chloride.